Welcome. In this video I'll discuss resistive wall modes, or RWMs, and these are a dangerous kind of instability for top-rack plasmas because they occur at high performance where we want the machine to operate, so the highest performance, highest fusion power, and these are driven by the pressure which we need to get fusion, and they're driven by the plasma current, which is also typically needed to get to high performance. So this combination of pressure and current drives an external kink, and so the entire edge of the plasma can twist and bend, and this can lead to a loss of confinement, so a disruption where the whole plasma hits the wall of the machine. So they can be stabilized in various ways. So rotation and the wall, conductive walls are two of the major ones, and these are related to the resistive diffusion of the field into the wall, and this can lead to something called mode locking, where the velocity or the rotation rate of the plasma suddenly stops on a very short time scale and leads to a kind of disruption. So discuss a little bit what's happening here. So we have a plasma inside a tokamak, so the plasma around like this, and there's somewhere outside the plasma is a conducting wall. And what happens is the edge of the plasma starts to kink or twist, and so you have some kind of a motion of the plasma. So it's sort of moving this way over here, and it's kind of twisting around, so it might be moving away from the plasma, or away from the wall at different locations, so it might be like this. And so what happens here is the magnetic field lines which are around the machine, as the plasma is moved outwards, these are compressed. And so the field lines which run kind of through here, they have a magnetic field. These are compressed, and so you end up with a higher magnetic field, a higher magnetic pressure, and these tend to make a restoring force on the plasma. Now what's happening at the wall is that there's a changing magnetic field, there's a changing flux through the wall, and so you end up with surface currents. So if you look at the wall kind of side on, so if you're looking kind of through the plasma, like this way, and you're looking through the plasma at the wall, here's the wall here. So it's just a section of the wall that's typically made out of metal, and then the plasma is behind us. And what's happening is the part of the plasma is pushing outwards, and so there's a changing magnetic field. There's a radial component of the magnetic field which is going, say, outwards, say in this case into the wall, and this is increasing with time. So you have a dB by dt, which is not equals 0. So you have an increasing or decreasing field. So the field could be out of the field of the wall, for example. And this changing magnetic field, obviously that means you have a changing flux. So if we take a loop around the part of the wall, so here we'll have an integral of E dot dl is again just the change in flux through the wall. So it's the change in the magnetic field over this surface here. And so when we have changing magnetic field at the wall, this will drive current, and the current on the surface will then produce a magnetic field which is in the opposite direction and cancels the field inside the wall. And so if you take a slice sort of through the wall, you'll have a current on the surface, and then no magnetic field outside that. So I'll try and draw that here again. So if now we look, instead we now look sort of this way, so looking down here, sort of side on through the wall. What we have is the wall is like this, and the plasma is over here on the left hand side. So you have plasma. What's happening is the field is pushing outwards, so we have the plasma edge, say it's moving out, and so there's a component of the magnetic field which is going into the wall. So going like this. This is driving a current on the surface. So yeah, a surface current here, which opposes the motion of the field through the wall. And so if you plot kind of the magnitude of the field change, so it's like delta BR, and you plot it against this distance. So here we have the wall location here, like this. What happens is we have a large current spike just on the surface, and so the field perturbation is largest inside the plasma, falls, and this is typically like r to the minus m, where m is the poloidal mode number. So it reaches the wall, and then the surface current actually reduces that to 0 inside the wall. And so if this was a perfect superconductor, the field wouldn't penetrate into the wall, and it would just be cut off at that location. And this then produces, of course, a field going in this way as well, and so you end up with reducing magnetic field and stabilizing the instability. What happens on longer timescales is that the wall has some resistance, and so this current sheet on the surface will slowly diffuse into the plasma. So you end up with a kind of slow diffusion of the current. As the current diffuses in, and as the current diffuses in, the magnetic field diffuses in as well. And so you end up with the magnetic field gradually going through into the wall. And so this resistive timescale then allows the mode inside the plasma to grow, and you end up with a resistive wall mode. So there are some things which can't be avoided here. So one way of stabilizing these would be to put a superconducting wall, but you need to have some gaps in the wall where you have diagnostics or heating systems, but also more importantly, you need to control the plasma. So if you have external coils which are controlling the shape of the plasma, the field from those coils needs to get into the plasma. And so if you have a superconducting wall, you can't control the plasma using external currents, external coils. And so the wall thickness is a trade-off between stabilizing the plasma and allowing external coils to get in and control the shape of the plasma. And so typically the modern tokamaks have thin shells because the feedback systems are better. Older tokamaks had thick conducting copper shells because feedback systems weren't very good, and the priority was to try and have a passive stabilization. Now with modern feedback systems, the wall can be thinner, and we can use fast feedback control to control the stability of the plasma. And so this kind of process happens on a much shorter timescale than for thick walls. But we can estimate how fast this happens by just using the form of this. So this integral here can of course be written also that we have just curl of E is minus dB by dt. And so what we can do is we can use inside the wall, it's just a conductor, so E is just eta times J, just for Ohm's law. And so J of course is related to B, so we have curl of B is mu naught J. And so we can put all this into here. And so we end up with the curl of E, so the curl of, and then if eta is constant, so if you have a metal wall with roughly constant resistivity, we of course just take this outside. The divergence of B is 0, and so this whole thing becomes minus del squared B times eta over mu naught. And then here we have dB by dt. And so we just have a diffusion equation. So now if the wall is thin compared to the length of the waves, or the instabilities in the plasma, then this is basically just the radial width. So it's diffusion across here, and this width here I'm just going to call LW. It's kind of the length of the wall, or the depth of the wall really. And so the second derivative here, this is roughly 1 over the wall width, and this time derivative is roughly 1 over the time scale, so tau W. So the time scale it takes the magnetic field to penetrate into the wall. And so we just rearrange this, and this gives the time scale is just proportional to the square of the wall size, because you have a del squared here. Then we have a 1 over eta. So as the resistivity goes to 0, for example, so if you had a superconductor, then this timescale will go to infinity. And so the higher the resistance, the the quicker the field penetrates into the wall. For typical values, this is sort of tens of milliseconds. Okay, so one thing which stabilizes these modes is plasma rotation, and the idea is very simple. That if you have a wave in the plasma, here I've drawn something going outwards, and here's sort of inwards at this point, and then maybe outwards here, and then maybe inwards here. So it's some kind of a wave. If this is spinning, then a point on the wall here sees the field first going outwards, and then inwards, then outwards, then inwards. And so there's an oscillating magnetic field at this wall. And so the current, instead of being constant, is now reversing direction. So you have an oscillating surface current. And if you have a surface current which is oscillating, it takes much longer to penetrate in, because it starts, imagine the current starts diffusing in one direction and then suddenly it reverses direction, and so it starts essentially cancelling out the early current that diffuses in. And so you end up with a sort of complex, much more complex diffusion pattern, but essentially it's a wave here into the wall. And what happens is if your rotation rate is high enough, the wall appears to be superconducting. So here I've put rotation rate, omega is the rotation rate of the plasma, and then this is the timescale, so 1 over the timescale. So this is like a frequency. So if you're spinning very quickly, then the wall appears to be superconducting, or it's approximately superconducting. And so many modern machines you can run, put very large NBI, so neutral beam injection in, and spin up plasma to very high rates. So MAST, for example, can spin a couple of hundred kilometers per second at the core. Larger machines are much more difficult to spin because they have much larger moment of inertia, and because you need to put higher energy beams into the plasma, and this reduces the momentum of the input for a given input power. And so the input power, although it's quite large, will not be enough to spin up future machines. And so for larger and larger machines, this becomes a problem because the wall stabilization becomes less good as it is in current machines. And what you can see as well is that if you start with a plasma which is spinning very fast, what can happen is that the small amount of resistance in the wall, so there's a current being driven at the wall which is oscillating very fast. There's some resistance in the wall, even though it's small, and this will dissipate some energy, and so there'll be heating in the wall due to the current, and this energy must come from somewhere, and the energy of course comes from the rotation of the plasma. And so as you drive the plasma, as there's some oscillation in the plasma, is driving a current, heating the wall, and the plasma rotation slows down. And as the rotation slows down, the wall appears more and more resistive, and so there's a runaway effect where the slower rotation leads to faster dissipation, and the faster dissipation leads to slowing down the plasma even quicker. And so there's a kind of runaway process which can lead to instability. It's called mode locking. And an approximate expression of how this varies is that the rotation of the wall, so this rotation rate, so how that changes in time, this is basically proportional to the current rotation times the time scale of the wall, and then the square of the radial magnetic field, and it's over 1. So here this is an approximation, but it's roughly like omega squared times tau wall squared. So you can see here that if the rotation rate is very high, so if this is very large, then this becomes larger than this, and this goes to essentially a 1 over a very large number. So this goes to 0 as omega tau becomes large. But as omega goes to 0, and so as the frequency rotation rate goes to 0, this also of course goes to 0. And as the frequency gets small, this term becomes small, and so it's roughly omega tau BR if omega tau is small. So if omega tau is small, then this is ignorable, and the whole thing is just linear. And so what happens is, if I plot here, So this is the magnetic field applied, so effectively the size of the plasma perturbation, and this is the frequency, rotation rate. So as the mode is small, it starts at high rotation rate, and so the drop in the rotation rate is quite slow. As this external field increases, the mode is growing, the plasma slows down quicker, and then eventually you get to the point where it will sort of lock, and the solution will jump to a lower solution like this. And what's happened here is that there's a bifurcation, so this curve looks something like this. And so what will happen is a plasma will go down here and then suddenly drop and then slow down. And what's seen in magnetic signals, for example, so if you plot, say, the field at a coil, so this is measuring like the time derivative of BR, this is time. So what happens is the mode starts small and grows, and it sort of gets bigger and bigger, and then the frequency sort of drops, and then essentially it seems to disappear. So the frequency starts quite high as the rotation rate is quite high. The frequency drops, so omega is getting smaller, and then appears to disappear. What's happened here is that not the mode has disappeared. What's usually happened is that the mode has been growing here. The frequency is dropping, and then eventually it's reached this point where it's locked. And so here we've locked, and so the rotation rate has basically stopped. And because this is measuring the rate of change of B, if there's no rotation, this doesn't measure anything. So there's no dB by dr. It's very small. And so what happens here is that the mode then penetrates into the wall and then goes unstable. So at this point you might find a plasma termination. So the plasma might disrupt at that point. Okay, so these are commonly seen experimentally. It's kind of growing oscillations in the plasma, which then lock and disrupt the plasma.